Hello, everybody. Talking about sustainability, mainly my project is about recycling wind turbine blade materials in concrete. Now, the wind turbine blade materials are really complex mixture with a complex materials combination, which makes it very hard, literally, to separate after the end life of those wind turbine blade materials. So now what I have on the left is what I can call it's a recycling chain, starting from mechanical recycling, which includes repurposing, cutting, shredding, and followed by chemical recycling, cement kilning, and landfill. That all of those are methods of literally recycling wind turbine blade materials. But it's worth mentioning that the first three, it's a delay for those materials to end up in a landfill. Unfortunately, majority of the company literally just jump straight away to the landfill for being a cheaper option. So now I will concentrate, in terms of my project, of PhD project, it's about cutting and shredding. So my PhD will partially participate in the recycling key chain in terms of wind turbine blade materials, mainly the GFRP. As you can see on the left-hand side, the materials have been provided from Vestas, then has been cutted to a certain geometry with a 50 mil length and 8.3 aspect ratio, and then mixed with a concrete in a different aspect ratio, 2.5%, 5% and 10%, to study the effect of those GFRPs on the concrete mechanical properties. So by talking about concrete itself is a very complex mixture as well. Any changes in the mixture will cause a different mechanical property. So what we did is we actually established two different batches. The first batch is we replaced the FRP needles with an aggregate, what we call it is as an aggregate replacement. And the second batch, which is B, we just added the needles into the mixture to study the both effects. So what we can see here for batch A, we had nearly 26.9% improvement in tensile property, while for batch B, which is the addition only, it has a gradual improvement. As much as you add more needles, we will have a better mechanical property in terms of split tensile strengths. It's just worth mentioning split tensile strengths are well-known mechanical testing for concrete. So batch B is one of the key findings in my project because the majority of the literature proposed a reduction in some elements of split tensile strengths. So now we have a win-win for batch A and B. Now, just as the fracture pattern for split tensile, it's really important to see the difference between both of them, where the traditional concrete has split in half immediately after a couple of seconds, while the FRP enhanced concrete is literally keeping the concrete mixture formed together, like in one shape. That will help in terms of earthquake or even enhancing or any split tensile strengths such as bridges where split tensile really needed. Now moving to the compressive strings. Compressive strings are one of the elements of checking the mechanical property of a concrete as well. Now for batch A, unfortunately we had a reduction for 7.5%, and that's to do with the replacement of the needles with the actual stone. So 2.5% volumetric replacement that caused a 7.5% reduction, while we are in a win-win side for the addition where we just add the needles in there. So we had a really good improvement in terms of compressive strings. This is one of the key findings of my PhD because majority of the literature shows a reduction in the compressive, and worth mentioning that reduction was the second key element for me to move off in terms of my PhD. I was always wondering why we always have a reduction in compressive in terms of my PhD and other literature review, other researchers, what they've done. So the key elements here is literally the surface bonding between the needle itself, which is the GFRP, and the cement is very poor. So I had to use Alicona machine to check different surface roughness elements, starting from no blasting, sand blasting, glass blasting. As we can see, the glass blasting shows a real improvement in terms of roughness. I've conducted a pull-out test. That pull-out test is literally well-known in terms of mechanical studying to record the bond strings between the GFRP and the actual concrete, which will help me later on in my modeling. I'm constructing a model with random distributed needles inside the cylinder to study the elastic modulus, compressive strings, and split tensile strings. Now the key finding is the surface bonding is the key improvement to improve the mechanical property of the cement. Establishing materials passport, it's really important to know where we got those materials and what kind of materials we have. In my PhD, I had to go through a series of experiments such as burnout test, moisture uptake, and all of sorts of materials. Finally, this could be a very good improvement in terms of a highway tunnel lining and runway. Thank you very much for listening. If you want to hear more information about my finding, I will be next to my poster. Thank you.